One thing about dynamic programming is the whole, the name is completely meaningless, and also doesn't tell you anything about what it actually is. And so just don't get too bothered by the name. It doesn't really reflect what it is. I think the easiest way for me, assuming you have had some experience with recursion, the best way to describe it is it's recursion with caching. And I'll use a recursion with memoization. Some people like recursion with caching or memoization, if you want to use a fancy term like that. And a good way to show that, I'm gonna be using Python for the code examples, and the reason is because I want to use some features of my debugger, which I think will help in illustrating some of the point. So let's run this program, and we get the answer 55. Okay, so okay, there's a very quick refresher on the Fibonacci, in case you didn't know. So Fibonacci is a sequence of numbers in which the nth element, so this is the first, this is the first one, second one, third one, fourth one, fifth one. Oops, no, fifth, sixth. The nth element is the sum of the previous two elements. So the first two elements are both 1, and then the third is the sum of 1 and 1, and the fourth one is the sum of 1 and 2, etc. That's how you build up the sequence. And this is a recursive solution that does that. To get the number at location n, whatever n might be, assuming n is greater than 1. If it's 2 or below, you return 1. If it's greater than that, I'm gonna get the numbers at the previous two locations by recursively calling myself to calculate them. Okay. Now this works, but it's a very inefficient algorithm to do this. Even though this is a very, very like classic example for teaching recursion, this is actually extremely inefficient. Does anyone have a clue as to why this is inefficient? Anyone?
It's like super nested recursion. So like
my instinct is also, is there some sort of like direct formula where you can go from n straight to, value that I don't know about?
That is true. That does exist. But we're not going to talk about that. There's actually a big O of 1 algorithm for calculating the Fibonacci number, but let's not talk about that. Let's pretend that doesn't exist. Or we're going to talk about this algorithm, but I want to sort of illustrate why this is extremely inefficient. One of the features of my time traveling debugger is that there's this utility called C calls that can allow you to see all of the function calls that happened in nested way. Okay, so this is actually what happened in order to calculate 55 at the end. So I'll just read through parts of it to lead you through what's actually happening. In order to calculate fib with n equal to 10, we're going to have to ask what's the result of fib with n equal to 9, and what's the result of fib with n equal to 8, which is actually all the way down here. So this guy is like, hey, can you calculate n equal to 9 for me and n equal to 8 for me? But in order to calculate n equal to 9, n equal to 9 has to know the result of n equal to 8. And then n equal to 8 has to know the result of n equal to 7, etc., etc. Until we get all the way down here, and then it's like, oh, it's obvious the result is 1. And well, I mean, the first thing you probably thought when I showed you this is like, this is a lot of stuff, right? Why is it a lot of stuff? And is this stuff necessary? And you can actually very clearly see that it's not necessary, because you can see a lot of duplication of stuff being calculated, recalculated. One example is here. This fragment here appears again over here. Not only that, this fragment here, it actually occurred here and here and later on here. So it's not just that there's recursion going on, but a lot of unnecessary calculation, because the same thing is getting calculated multiple times. N equals 4 is getting calculated here and here and here and later on here as well, you know. But at the top level, like, well, n equals 9 calculates n equals 8, but n equals 8 is asked for again. So anyway, the point is, there's a lot of redundancy of work, and that can easily be eliminated via caching. So let's do caching, right? So we're still doing recursion, but we're just going to add in caching. And the way I'm going to add in caching is just by saying, hey, I'm going to make a dictionary. Each key value pairs is the key is the input and the value is the output. And I'll even put in the first two values, which is the first element should give you 1 and the second element should give you 1. If I did that, I don't even need this if statement anymore. I just say, hey, is n in the table? If it is, just return your cached value. I should return it. And once we get the answer, I'm going to stick it into my table so that it can be reused next time that same number is asked for. So I'm going to put the key is the input, which came from here, and then the value is the answer. And then at the end, I still want to return the answer. So we've added caching, aka memoization, to this recursive algorithm by just changing a couple of bits here. And if we run this again, we get the same answer, but now we get this graph, which is much smaller, which means the computer had to do much less work. So yeah, so that's recursion with caching. And hopefully that just gives you an intuition of what dynamic programming is. When you read the literature on dynamic programming, there's what they typically say is there are two conditions for dynamic programming, two conditions under which if these two conditions held, then you know a dynamic programming solution is a good one. And those two conditions, one is they call it optimal substructure. Optimal substructure. What a word. Did I spell this right? Yeah. Okay. And the second one is overlapping subproblems. And I'll just briefly explain what these means. Optimal substructure, all that means is that the optimal solution, or in some cases, the optimal solution just means the correct answer or correct answer. And when they say optimal solution, they say it because a lot of times dynamic programming is used in problems where you're trying to find the absolute best solution out of many possible solutions. That's why they use the term optimal solution. In the case of Fibonacci sequence, there's only one correct answer. There's not many answers to choose from, and then you have to pick the best one. There's just one answer. In any case, what optimal substructure means is that the optimal solution or the correct answer depends on depends on optimal solutions of subproblems. So if you had the optimal solution or correct answer of your subproblems, then you can use those answers to derive your optimal solution of your parent problem. And more or less, what that means at the end of the day is you can use a recursive solution to solve the problem. What does overlapping subproblems mean? Overlapping subproblem is actually exactly what you saw when I did this without caching. I'll do it again. This is a very concrete display of overlapping subproblems because the same subproblems are needed by multiple parent problems. So the concrete cases are, well, the fib of n equals 8 is a subproblem that is needed by n equals 9. But n equals 8 is also a subproblem over here that's needed by the original parent, which is fib of 10. Fib of 10 needs fib of 8 and fib of 9, but because fib of 9 also needs fib of 8, overlapping, that this guy, yeah, overlaps with that. And because of this overlapping, if you don't do caching, you're gonna get a lot of redundant and unnecessary calculations like we're seeing here, and the caching just eliminates that. Okay, any answers? Sorry, any questions at this point or comments? Okay. Okay, the next thing to say is whenever you have a dynamic programming solution, you can either build the solution in two different ways. And you can always convert between these two ways. So two ways to solve DP. The first way is what you already saw, which is recursion with caching. The second way is called bottom up. And the way bottom up works is instead of, and bottom up doesn't even require recursion. I'll show you in a bit how that works. Because you know that sort of, with prior knowledge, the order in which you're gonna need the solutions of the subproblem, instead of starting at the top at n equals 10 and go downwards in this tree, what you can do is actually go in reverse direction. Start at the bottom with n equal 1 and just say, hey, I already have the answer to n equal 1 and n equal 2. Now let me calculate n equal 3 and n equal 4, and those are easy. So when you get asked, hey, what is the 10th number in the Fibonacci sequence, all you're gonna do is you're gonna allocate an array. Use this box here. You're gonna allocate an array of 10 numbers. Okay, is that 10? Yeah. And then you already know the first two are gonna be 1. And then you're just gonna do, I fill this in, add the previous two numbers together. What's the next one? And then you're done. And there's no recursion involved. All you do is write a little loop to do this. And you can, you subtract 1 and subtract 2 from the current index, etc. It's very straightforward. But not all problems will end up with a one-dimensional array. Some problems may end up with a matrix, that's n by m. There might even be three-dimensional ones, depending on the problem. But a simple problem like Fibonacci, you just end up with a one-dimensional array. You filled it up, and then you just return the last value from the array, and you're done. Okay. So that's DP with the Fibonacci sequence. So let's do a different problem. Okay. There's a problem called is it the coin change problem, I believe? Let me see. I think on lead code, there's a coin change problem. Yeah. Okay, so this is the coin change problem, and it's basically saying you given a dollar amount, and let's say, I don't know, you have to make change for 475. How are you going to make change for that? You have these denominations. The denominations are given to you as an array of numbers. Maybe instead of like using decimals, we could just do it in terms of cents or something, so that we don't have to worry about decimals. And then so in the standard US currency, what we probably have is like 500, 100 for $1, 25, 10, 5, and 1. And then you are allowed unlimited supply of denominations of each type. So you don't have to worry about running out of quarters and stuff like that. You just assume there's unlimited amount. This particular problem asks, what's the fewest number of coins or denominations that you need to make up that amount? How do you make change for this? So can somebody answer this? Like, how would you make change for this?
What's ideal change? Like 4 1s and 3/4? Oh, you're just trying to get the smallest amount, right?
Yeah, the smallest number of either coins or bills. The smallest number of stuff that you have to hand back to the customer, I guess.
2 $2 bills and 3/4.
$2 bills. Okay. $2 bills inserted. But how did you do that? What algorithm did you use to
I used my familiarness with the American currency. Yeah.
But that's not a teachable thing. You can't just say just do it. You can't.
That's
Like,
true.
if somebody doesn't already know how to do it, you can't tell them just do it. So what algorithm would you use to do this?
I would probably do like a while mod not equal 0 type of deal.
Right.
Assign the remainder to some variable
Mm-hmm.
and do that like de-escalating from the highest denominations to the lowest denominations until the result is 0, or the input is 0.
Okay, very good. Yeah, that's how I would do it as well. I start subtracting starting from the highest denomination. And well, this is not going to work for the $5 bill. So I move on to the $2 bill, which is going to work twice. So I will have 2 times 200, which will get us down to 75. And then we'll try the 100, not going to work. And then we're going to go to the 25, and we'll end up with 3/4. And we'll end up at 0. So at the end, we have 5 denominations to hand back to the customer. Is that the best algorithm? And I'll show you the code for that because I already wrote that up. I kind of gave it away by the name of my algorithm. Oops. But is this the best algorithm?
Let's see. So the criteria that you gave before is I want to use the actual terms that you used for the criteria, but
well, I wanted fewest number of coins.
well, you said for when you wanted to implement caching, right? So
Well, right, like the caching is like our dynamic programming. What even makes us turn to is this a dynamic programming algorithm, first of all? No, it's not. It's not I guess it could be expressed in a recursive kind of way, but I'm not using any kind of table to cache any intermediate results. I'm not doing that. So this is actually a greedy algorithm, as the name of my file shows. And the reason it is greedy is because while at each stage, I could have chosen from a number of different choices. I do not do that. Instead, I always make a educated guess and go with only that choice based on the educated guess. And the educated guess is I'm always going to go for the largest denomination at any given moment until that runs out, until that denomination doesn't work anymore. I'm always choosing the largest, whereas I could have chosen any of the denominations at any point in time in making the change. Like why didn't I just choose a penny at the beginning of making the change? I didn't because I kind of intuitively knew that I would end up with a lot of coins. So I didn't do that. Are there cases though in which this greedy strategy does not give you the best solution? Well, I'll tell you the answer. The answer is in the denominations that we have in the US, the greedy strategy is always optimal. so in order for you to get a situation that it is not optimal, we have to go to maybe a different country. So let's say we live in a country where the denominations are 5, 4, and 1. And then we had to make change for 8. So now if you use the greedy strategy, we would say, hey, I can take 1 of 5, leaves me with 3. And then to do 3, I'm going to have to do 3 ones. Oops. I'm going to have to do 3 ones. I'm going to end up with 4 coins. But there's a better solution for 8 because there's 2 times 4. So I would only end up with 2 coins. So in this fictitious country where their denominations are 5, 4, and 1, the greedy algorithm is not the optimal solution. Okay. Now, I kind of have to sort of be creative to come up with a situation like this, but use your imagination. So things like this can exist. It can exist in other domains as well. Although, making change is probably not the most pressing problem. It's for an exercise. So now the question is, now that we know that this greedy algorithm won't give us the best answer, we're gonna need something different. We're gonna need to not only try the largest denomination, we actually potentially need to try all the different possibilities. So like given 8, we can, and again, the denominations are 5, 4, and 1. We can structure this recursively. Step 1, I'm going to choose 5, 4. I might just try all of the different options and see what I get. If I choose 5, I end up with 3. If I try 4, then I end up with 4. And if I try 1, then I end up with 7. And for 3, well, 4 and 5 no longer work. So I have to do like 1 to get 2, 1 to get 1, and then 1 again to get 0 at the end. And then with 4, I could either do 4 and be done, or I have to do 1 and get 3, and then I have to do 1 to get 2, 1 to get 1, and then 1 to get 0 again. And then when I'm at 7, I have 7 left. There's more work to be done. I'll let you imagine the rest because it gets slightly tedious over here. But the point is, there's all these possibilities I might need to do. One of the points I'll make is you can clearly see a overlapping subproblem, which is this one versus this one. I have 2 remaining, and I need to make the change and give me the optimal change. And that overlapping subproblem will probably show up somewhere around here as well, maybe multiple times. And when that happens, that's a good candidate for using dynamic programming. Yep. So maybe we should try to implement that. Okay. Okay. So let's do the recursion with caching. So let's do coin change. I get the coins and the amount. And the coins is just an array. So I'll end up calling it probably like coin change 5, 4, and 1. And then the amount, I used 8. Okay, something like that. And maybe I'll get the answer here and print it. The answer should be 2, I guess. The optimal choice is 2 of the $4 coins or something. Okay, so how do we do this? We want to try all the possibilities. So for each coin that is a possible denomination, I'm gonna try ticking this coin. And so if the amount of the coin is greater or equal to the current amount, then I'm gonna use this coin, basically peel it from the amount. So remaining. Should I call this let's call this remaining. Although no, I'm just gonna have it inside here. Okay, so if I take this coin and I get this remaining value, I'm gonna recursively call myself. Same coins, but with the remaining amount that as a result of taking this coin. And then this is the number of coins. This is the number of coins from this calculation of the subproblem. But because I took 1 coin here, so my num coins, I should add 1 to mine. Does that make sense? Or maybe I could just do it inline like this. So assuming this, because this is recursion, and because we have optimal substructure, I'm gonna assume that the result, whatever this recursive call return, is the optimal number of coins for this particular subproblem. So therefore, if I add 1 to it, that's the solution for if I were to take this coin. But I'm gonna try that for all of the possible denominations. So out of all of these, I'm gonna get this num coins, and I want to get the best one. And a simple way to do that is just make a best variable on the outside. Or I could just collect all of them and then just do a min on everything in the array or something. But I could also just have a best one on the outside and say maybe best is just okay. I'll just make best is none. So if best is none or num coins is less than the current best, then best is the new num coins. So if it hasn't been initialized yet, then the best gets this num coins. But if there is an existing best, but my num coins is better than that, I update the best. Make sense? And then I return the best at the end. Does that work?
It looks right.
It looks right? Okay.
Yeah. I think so.
Is there Sorry, I was looking at something else for a second, but are you handling the case where, what if the amount minus coin is less than 0?
Oh,
if coin is greater than amount, never mind.
But there is a case of else what happens. And I haven't really considered that. So if, well, I just wouldn't do anything, I guess. There could potentially be a case where none of the coins will work anymore. There could be a case, where you have an amount.
That would just be none.
It could just mean amount is 0 at that point, but it potentially, depending on your denominations, like if your denomination doesn't have a 1, for example, and your amount is 1, then there's no way to make the change. So, and you probably want to have some way to indicate that there's actually no way to make this change because we don't have a coin that's small enough for some reason in that country. Not likely, because I imagine most countries have a penny as one of their denominations.
Throw an error or something if you want. But
right.
Yeah.
But I think we do have a problem in that we didn't check for amount might be 0, in which case none of the coins will make. And what's that going to happen? I don't know. Let's see.
Or is none
none
Python keyword?
None, it's a Python keyword, means null, the same as null.
Gotcha. I'll just say best equals 0 then, because an amount of 0, you don't need any coins to make change for it. Isn't that actually pretty safe if we're assuming that we can always make change for any real amount?
The problem is 0 is going to be less than anything. So we're going to... Because here we're saying the best is the smallest, and 0 is even smaller than that.
But oh, never mind. It's reversed. Yeah, I see.
Yeah, okay. We could make this max int or something, but
so it'd be null.
Yeah,
best is none, then it's 0.
Yeah, just do it like this. Wait, why are we getting none now? I'm not sure. Let's debug. Okay. If coin is greater than the amount, coin is 5. That's wrong, isn't it?
Oh, it's less than or equal.
It should be less than or equal. Okay. We're trying to add int and none type. We're returning the none type, presumably because none of these iterations hit, probably. With the debug. Okay, so this is, we'll go back here.
It's probably because at some point you're going to try to add 1 and null, and it seems like Python isn't cool with that.
Right, but how do we get the null? Because the reason it would be null is because we returned best, and best was still null, right? I'll go back to the point. So that would be this point. So if I go back, we return best, which was none. But how do we get that?
Because at some point, like 5's not going to work.
So the amount is actually 0. We found. So the amount in this iteration of the function, the amount is 0. So there's not going to be any coin. I'm starting at 0, but that was because somebody called it with 0. Namely here, the remaining was 0. After we subtracted the the coin 1 from the amount of 1. We ended up with remaining 0, and now we're trying to make change for 0. We didn't have anything to handle the 0 case. Amount equals 0. So if amount equals 0, we go through it. We end up with best equals none, and we return none. That's not going to work. We could just, if it's in the case of none, we could just return 0 at the end. Just add a little if statement here. So we could do that.
Seems right. Then you handle the 0 case too.
What would oh you're saying just do it up here?
Oh, I mean, no, it doesn't matter to me, but yeah, that would be probably more elegant, I suppose.
Yeah, I think this is more obvious when people are reading this code. This would, okay,
Yeah.
let's go with this. We get 2, which is correct. Whereas we use the greedy one. We got 4. Yeah, so this is the gives the more optimal answer. However, oops. However, we get this situation where let's see, where are the overlapping problems? We're asking for 3 here. We're asking for 3 here again. We're asking for 3 here again. And we clearly ask for the same thing multiple times. And that's inefficient. We're wasting CPU, right? So what we do is we add a table. No, putting a global table is probably not good for this problem because in one instance you might get one denomination set. In a different instance, you might get a different denomination set. So a global table doesn't really make sense. So maybe what you want to is pass in a table, and you just initialize the table and pass it in here. And I'll pass it through to the recursive calls. And then here I'll do a lookup and say, hey, if the amount is already in the table, return the table amount. And when we do calculate the answer, and this the best is the answer, I will say put it into the table. Yeah, now we get much shorter execution. Make sense? Now, just for fun, if you, any questions first before I go to the next thing? Like any maybe like any thoughts seeing this? What are the things that occur to you when you're seeing this dynamic programming, or maybe have you read about dynamic programming in the past, and what were your thoughts about it?
Seems like it can get pretty memory intensive, so you probably want to make sure that it's, yeah, I guess worth that trade-off.
Yes.
Plus that you are paying for lookups constantly, so it seems like you definitely have to cross a threshold for it to be worth it.
Yeah, that is true, because if I fill up a table with tons of data, that's going to take up memory, takes it away from other parts of your program that might need to use memory. One particular like a real application, real scenario where the memory might suffer is that there's actually a parsing algorithm that is based on dynamic programming. it's called the early parsing algorithm, and it's based on the dynamic programming in that it creates a table, and as it's parsing character by character, it puts entries into that table for every character or every token that it encounters. If you tokenize your string first, then it'll be per token. But what that means is the longer your input is, the larger that table needs to be to hold up all of your tokens. And so how do you compare this, like the dynamic programming version to the greedy version? What are the pros and cons then?
The greedy one didn't get the right answer.
The greedy one can get the right answer.
Well, didn't get the right answer.
Didn't get the right answer. But is there anything good about the greedy one?
Well, one advantage is just in general, it's more overhead to set up caching. So, sometimes for clarity, it's better to have a simple algorithm, even if it's more inefficient in practical use cases. So I think that kind of goes back to Jason's point, where he was talking more like technically in terms of like crossing that threshold. I always value readability, and there's another if statement and another setting up of a table and another argument in the dynamic version.
Okay, the code complexity is more in.
But I guess it doesn't really matter to me if the code complexity is more or less if the algorithm doesn't solve the problem.
Right. Well,
Are you comparing the two recursive ones, like one with dynamic programming and one without, or are you comparing literally like the one that works and one that doesn't?
The one that works and the one that doesn't. Is there anything good about the greedy version over this quote unquote better one?
To be fair, I think there are situations where an algorithm that doesn't give you the always exactly correct answer could still be a good choice when you don't need exactly the correct answer. A good example is pathfinding algorithms. A* is very fast, but it doesn't always give you the most efficient path, but it's way, way, way faster than something like Dijkstra's, which will get you the shortest path guaranteed, but takes a lot longer.
So the benefit is speed, basically.
Right. You sacrifice a little bit of accuracy for a lot of speed.
Yep.
Yeah. Greedy still makes correct change. It's not like it's going to unbalance your financial books.
Right. Yeah. So greedy is faster, and also it uses less memory, as Jason already mentioned. Yeah. Like I said, I don't know if I want to go through. We only have 5 minutes left. I don't want to know if we could rewrite this using the bottom-up approach as well. For any given dynamic programming algorithm, you can either write it this recursive way or write it the bottom-up table-based way. But since of the time, I'm not going to do that, and we'll just leave it here.